Hi, welcome to video number 3 documenting this instrumented telescope project. There have been a lot of changes since the last video, but probably the biggest headline change is this, which is that the main brain of the system, the computer, is now a Raspberry Pi, and this is a Bluetooth dongle, which means that we can now communicate with the laptop without any wires, which is really nice. This is just a big battery, which I'll use to turn it on. The LCD screen now is mounted here. You can see it's just printing out the coordinates, and it's mounted quite nicely, near the eyepiece, so you can easily see what's going on. In this video, first of all, I'm going to demonstrate the basic functionality of the iTelescope system, which viewers of the previous videos will already be kind of familiar with. Then I'm going to show a demonstration where I use the iTelescope system to target a specific object in the sky. Then in the second half of the video, I'm going to go into the details a little bit. I'll talk about why I'm using the Raspberry Pi, and also show you the user interface software on the laptop, and give you some of the details on the calibration of the iTelescope. So just to demonstrate the main functionality of the system, you can see on screen here on the laptop Stellarium virtual planetarium software, and this reticule down here indicates where the telescope is pointing. I'm just going to go now, move the telescope, and hopefully you'll see the reticule moving too. Right, now I want to show you a demonstration where I use the iTelescope system to target a specific object in the sky. I made this video last night in a little bit of a hurry when I realised that the moon was really nicely lined up with my window. Here I want to show you just a really simple demo of using the iTelescope system to point at an object. I've chosen the moon here because it just so happens that it's lined up really nicely with my window right now. So I'm just going to move the telescope and try and steer the reticule onto the moon. So using the zoom, I should be able to show you the reticule is now aligned on the moon. And now I'm just going to bring you around the back of the telescope to show you the view out my window. And I'm going to kill the lights and show you the view down the eyepiece. And if I can get it focused, there is some moon. Well, that demonstrates what the iTelescope system does. Now I want to go into a little bit more detail on the updated design of the system. I'm using potentiometers mounted in the base to measure the movement of the telescope in its two axes, which are altitude here and azimuth here. If you're interested in learning more about the exact sensors used, then please see my first video linked here. The position sensors are then read by the Raspberry Pi, which, as I've already mentioned, replaces the Arduino which was used on the old design. So there's a couple of reasons why I'm using the Raspberry Pi instead of the Arduino now. First one is the fidelity of the analog digital conversion. So this board here that you can see here mounted on the Raspberry Pi, this is an ADC Pi breakout board which has a 17-bit analog digital converter, which means the precision of the angular measurement is higher using this. And the second reason is that on the Arduino you can only do floating point calculations with decimal precision of about 6 decimal places, which isn't really enough to do the astronomical coordinate conversions on the board itself. You don't actually have to do them on the board. You could do them on the laptop, but I quite like to have the system a standalone system where you don't need the laptop in order to be able to do the coordinate conversions and print them out on the LCD screen. Aside from the Raspberry Pi, the other major update is the software, which has been completely rewritten from the ground up in Python. I'm in screen capture mode so I can show you the user interface running on the laptop. This allows you to change settings on the telescope and also manage the connection between the telescope and Stellarium. So the program begins with this splash screen and commences a search for the telescope's Bluetooth. Some of the settings that need to be changed on the telescope are the location and the current time. So to set the location, I select option 1 from the main menu. It prints out the current latitude and longitude and gives you the option to change it. So I'll select change location. And now you can enter a new latitude and longitude, and it gives you options for various formats. I'm just going to use degrees, minutes and seconds here. And when that's done, the telescope's LCD screen will print out the new latitude and longitude, so you can use that to confirm that it's worked. Option 2 on the menu allows you to change the time. In fact, whenever you connect between the laptop and the telescope, the clock on the telescope will automatically be synced with the laptop's clock, but if for some reason you want to use a different time, you can use that menu there. Option 3 is for connecting to Stellarium. We'll come back to that in a minute. This is option 4. Now this just prints out the current right ascension and declination of the telescope. This can be useful as a sort of sanity check to convince you that you've got the system set up correctly. Now option 5 is a calibration. This is for if you're moving the telescope around and you want to be able to put it down in a field somewhere and not spend ages trying to align the mount. Instead you can do a software-based calibration using known stars. The calibration works using Stellarium. So here the menu gives you a host name and a port number, which you enter into Stellarium when setting up the telescope, and you can change these if necessary, but they're correct here, so we'll just connect. So in Stellarium you should see the reticule appears. So what you have to do is point the telescope at a known star and then select that star in Stellarium. And if you do this just once, you get an azimuth only calibration, so that's just calibrated the azimuth there. And that's fine if you're confident that you've got the base on level ground, but if not, then you can just repeat the process with a second star and then you get a full azimuth altitude calibration. So to connect to Stellarium normally, just select option 3 under the main menu, and it's the same as before under the calibration. You have a host and a port, press connect, and hopefully, yes, the reticule then appears on the screen where it was before after the calibration. And that's it, you're now ready to use the system. So that's basically it for this video. As usual, the software all the software for this is open source and online. You can download it from my website. I've left on there I'll leave up the software for using the Arduino as well. Although if you're interested in using the Arduino along with Stellarium for your own project, I recommend taking a look at Leon Rosengarten's project on YouTube. He's still using the Arduino and has done quite a bit of work with that. Kudos and thanks also to Prasanth Nair. His angles.py library was really useful in the building of this. Also John Shipman, whose sidereal.py library, again, was really very useful. And finally, thanks to Toshimi Taki, who the maths on his website was the starting point for the calibration calculations that I used. And finally, thanks to all the people who have commented on the videos and sent me emails about this project. It's really great to hear from you and learn about the other cool projects that people are working on. If you like this, please visit my website for more info and to download the code, and remember to subscribe if you want to see the next video. Thanks.